I want to thank everyone for joining us today from wherever you're at, whether it's morning, evening, or afternoon for you. Thanks for joining us for this Global Power System Transformation Consortium Community of Practice event. This is held in partnership with our regional lead organization, the ASEAN Center for Energy. So today the topic is advanced renewable energy forecasting, and we have a great set of presentations for you. So before we get started, I'm going to cover a few housekeeping items about this Zoom platform. So this webinar is being recorded. It will be shared with attendees. You'll be able to find it on the Global Power System Transformation Consortium website. That's globalpst.org, on our YouTube, and we'll also send out a follow-up email so that everyone has access to the recording. If you're having any issues with your audio, you can listen in by two different methods. So computer audio, this is sort of the standard default option. If you're having any issues, just check, you can kind of hover over your toolbar and check audio settings. It's on the, I think, left-hand side. And just check your sound output and volume and make sure you don't have like a Bluetooth speaker that it's coming through somewhere in another part of your house. Otherwise, if you're still having issues, you can try to dial in by phone. The dial-in numbers can be found in your registration confirmation email. So if you're having any audio issues, just try the opposite audio method of what you originally tuned in by. If you want to have, we will have a Q&A session at the end of the presentations. I want to note to everyone that there is a specific Q&A question and answer function in your toolbar. This function, we would like everyone to direct their questions through that Q&A function. Please feel free to ask your questions at any time, and then we will address them after the presentations. And I want to note that the Q&A function is distinct from the chat. We'll keep an eye on the chat as well, but please try and put them in the Q&A if possible. It helps us keep it a little bit more organized. And to that end, if you just have a comment, if you just want to introduce yourself or say hello, feel free to use the chat. There is a chat available, and just make sure to send it to everyone so that we can all see it. So I will cover a few just the agenda for today. So we will have an introduction by Beni from the ASEAN Center for Energy. We're going to have an overview, our three technical presentations here, an overview of advanced renewable energy forecasting from Bri-Mathias, sort of a Vietnam-specific context for RE forecasting from Lynn, and then the Australian context as well, and then our Q&A session at the end, as mentioned. So with that noted, I will go ahead and hand it off to Beni to, again, Beni is our moderator today. He is our master of ceremony, and he is with the ASEAN Center for Energy. So Beni, feel free to take it away.
Thank you very much, Isabel. I hope my audio is working well. Hello, everyone, and good morning from Jakarta. Warm greeting to all of you, wherever you are joining with us now. And also, I would like to welcome all of you to the webinar of GPST ASEAN Community of the Practice today. System operators are faced with many challenging questions as they model and forecast variable renewable energy generation for the complex transformation power system. This event, hosted by the Global Power System Transformation Consortium, will focus on the deeper dive per learning and the good practice to support advanced renewable energy forecasting and the role of advancing forecasting in the power system transformation. You haven't seen the agenda before, where we will bring together system operator to share the experience on this topic and discuss the specific challenge in the Southeast Asia region. And also mentioned in the housekeeping, if you have any question, feel free to select the Q&A features, and then we will address it in the end of the session. And as kindly introduced by Isabel, I am Beni Suryadi from the ASEAN Center for Energy. I am leading the research and program on the power sector at ACE, in tandem with the expert from all of 10 national utilities in ASEAN countries. including on the development of the ASEAN Interconnection Master Plan studies, a regional blueprint for the cross-border electricity interconnection in the Southeast Asia region. And I'm also a co-member of the G-PST Consortium. So in the agenda, we have excellent speakers who are joining with us today. First, I'd like to introduce you with our first speakers is Dr. Bri-Mathias, Hodge, who is the Chief Scientist in the Power System Design and the Planning Group at the National Renewable Energy Laboratory, and a distinguished member of the research staff. He is also an associate professor in the Department of Electrical, Computer and Energy Engineering, and a fellow of the Renewable and Sustainable Energy Institute at the University of the Colorado Boulder. Next slide, we have Mr. Lynn from the National Load Dispatch Center of the Vietnam Electricity. He is an expert of the Renewable Energy Management Department, a new department that was established at EVNNLDC to be responsible for the management and operation of renewable energy resource in the power system in Vietnam. And we also will have two experts from the Australia Energy Market Operator, or AEMO. First, we have Mr. Jack Fox, who is an operation lead within the operational forecasting team at the AIMO, leading work to overhaul the core forecasting system used for the short-term load forecasting and wind and solar generation forecasting. Another one, we have the second expert from AIMO is Mr. Joshua Brodrick, who leads AIMO data science team within the operational forecasting, where they are responsible for the development and implementation of the new machine learning technique for both operational grid demand and wind generation forecasting, as well as advising and leading strategic analytics and the project work. So it's a good lineup of speakers for discuss our topics today. But hopefully many of you are already familiar with the GPST, but if not, I want to provide a quick introduction to kick off our webinar today. The Global Power System Transformation Consortium, or GPST, is all about the deep collaboration with the system operator around the world on the cutting-edge research to bring the highest level of the variable renewable energy onto the grid, as well as the provision of the technical assistance, knowledge sharing, and peer learning on the proven operational and engineering solution to advance renewable energy integration in the unique context around the world and to address a key challenge. Through the GPST, we are working with the many partners across all the region of the world. And on this graphic, in the middle of the slide, you see our funding system operator, or FSO, which include AEMO in Australia, National Grid in the UK, Airgrid in the Ireland, the EnergyNet in Denmark. We have KESO and ERCOT in the US, and they are really focused on coming together to identify the most cutting-edge research area and related research and development investment required to reach a very high PRE, as well as working with the peer system operator globally to support them in scaling the
Did we lose Beni?
Yeah, it looks like we've lost.
Certainly sounds like it.
Okay, hopefully we get Beni back. I'll message him in the meantime. But I think maybe
we can probably just transition on and I can start. And then when he jumps back in, we can get back into that. And hopefully he's back on by the time we transition.
I think so, yes. So we'll go ahead and just to wrap that up, if there's any more information you'd like about the GPST, certainly visit globalpst.org or reach out to us. So In the meantime, we'll go ahead and we'll get started with Bri-Mathias's presentation, and hopefully we get Beni back on the line. So Bri-Mathias, feel free to take it away.
Thanks so much, Isabel, and very happy to be here today and speak to everyone. So my goal here is to just give a real overview of advanced renewable energy forecasting techniques and how they can be utilized in power system operations to really just set things up for a lot of the folks that will follow. Next slide, please. So I'd like to take a step back and just look at the power system basics and understand really what the goal here is. The goal is to have supply meet demand at all times, right? And the reason why this is challenging in the electricity system is because this has to happen not only continuously, but instantaneously. And lots of things can happen during those different time scales. Loads can come on and off, generation can turn up and down, especially as we add more renewable generation, which PV and wind are variable and uncertain. It gets a little bit tougher to do that because we don't know exactly when they're going to ramp up, ramp down. And so really we're trying to be able to provide information so that we can make decisions now about future states. And so forecasting really plays a central role in that. It allows us to look ahead and decide what actions we're going to take in a future time frame with less uncertainty than we would have without it. And so we can't do a whole lot about that variability of those resources, but we can work on that uncertainty. And that's really where forecasting plays a huge role. Next slide, please. And so I just want to talk a little bit about a couple different terms you might end up hearing when it comes to forecasting and be able to talk about sort of, start out on a solid foundation. So often the forecasts that we talk about within power system operations are known as point forecasts. Sometimes you'll hear this referred to as deterministic forecasts, right? So this is tomorrow at noon, there will be 50 megawatts from this solar plant, for example. Now, this has advantages and disadvantages. This is simple and easy to understand. We are predicting the power output there. But there is always some sort of error there, right? We're usually not exactly correct. And sometimes with some operators, this can sort of erode confidence, right? Maybe what looks really good to a forecaster, where you're predicting a up ramp to come at a certain time, the forecaster may think they got that right because they were only off on that ramp by, say, an hour. Whereas from the system operator's perspective, if that comes an hour earlier than they were expecting, then that's a missed forecast. And so we really have to be able to look at it from both the system operator's point of view and the forecasting point of view, and really try to bridge the gap between the meteorological community and the power systems community to make the most sort of value out of the forecast that we do have. The second type of forecast that there is out there is known as probabilistic forecast. So this tries to take that uncertainty in the forecasting information and provide some sort of quantification of it. And so the good thing about this is it does give you a little bit more information. It's not just there's going to be 50 megawatts at this plant tomorrow at noon. There's a 90% chance that there will be at least 50 megawatts at this plant at noon, for example. There will be a probability of exceedance forecast. And so the good thing about this is that it does provide more information that can be utilized by the operator. The hard part about it is most of the different processes in power systems in which we use forecasts haven't been designed for probabilistic forecasts. And a forecast is only as good as the decision it allows you to make, and therefore only as good as the decision-making process that you incorporate it into. And so, probabilistic forecasts are perhaps not the most intuitive thing in the world, and it takes some practice to sort of understand and to look at what the different processes that they could be incorporated into and how those decision-making processes might change with probabilistic forecasts. So just to give you a little bit of an idea about some of the things we talk about with point forecasts, it's generally we talk about error metrics. We talk about root mean squared error. We talk about mean bias error. We talk about mean average error. With probabilistic forecasts, we talk about more components. We talk about things like continuous rank probability score. So this is a combination of two things. One, calibration, or sometimes called reliability, and two, sharpness. So reliability is really, if you say something was going to happen 1% of the time, does it actually happen 1% of the time? And obviously you need a long time frame to be able to make accurate evaluations of that. The second thing is you could just take the history and say, these are the probabilities of an event coming by taking a very long history, right? And that's going to be very reliable, but it doesn't do you a lot of good because at any one time, you're looking at any event that could happen, and it's not conditional on the current weather conditions. And so what this is sharpness. You want a forecast that's reliable, but as sharp as possible. So as small of a spread in it as you can get away with at that particular time. Next slide, please. So a couple other things, there's a lot of time frames involved with forecasting terminology. And so I just want to set some of these out, on a common basis to start with. So often you'll talk about a forecasting run from a numerical weather prediction model, which we'll talk about a little bit more here in a little bit. And so you have the issue time. This is the time when it actually, gets sent out. Then you have the lead time. How far in advance of that issue time is it? So for example, at noon today, I send the results that start for 4 p.m. And then they cover a certain horizon, which is let's say 4 p.m. till midnight. So an 8-hour horizon. This also has a resolution. How granular is that forecast? Is it every hour? Is it every 15 minutes? Is it every 4 hours? And so also with forecasts, we have to understand that this isn't static information, and we always want to be able to utilize as current information as possible. And this is why you also have update rates. So some of these large numerical weather prediction models only update, say, every 4 hours. Other forecasts may update every 5 minutes at the dispatch timescale for very short-term forecasts. And so there's a lot of different timescales associated with forecasts. And just to make sure that everybody's on the same page and you're sort of comparing apples to apples, it's always good to really define these terms: the resolution, horizon, lead time, update rates, and issue times, and so forth. Next slide, please. And so how are forecasts actually produced? Well, it depends on the timescale that we're talking about. Within operational forecasting, they're what I would call sort of ultra short-term forecasts, which is within an hour or out to maybe 2 hours ahead. And these are generally created from statistical or machine learning methods that utilize small amounts of, they utilize recent historical data in order to make a forecast over those smaller horizons. This is because numerical weather prediction models, which are physical dynamical simulations of the atmosphere, require quite some time to run if we want to do that at high resolution, both temporally and spatially. And so after about, say, 4 hours ahead, most methods will rely on these physical methods, and those go out days ahead to weeks ahead. Now, often what will happen is you'll have some statistical methods applied to that later to, say, downscale it or correct for a bias. And so it's really a combination of physical and statistical methods that often get utilized in practice. And that sort of midterm or short-term horizon, say 4 hours ahead to 2 days ahead, is one of the most common places for the application of forecasts, in that generally aligns with the unit commitment and economic dispatch processes. All right, so one term you might also hear in forecasting is ensemble forecasting. And this is the idea that the more forecasts you have, if each of them will provide a little bit different information. And so if you say, for example, take an average of 50 different numerical weather prediction model forecasts, you're more likely to get a lower error than if you only utilize one. To take that same example of, say, a wind ramp coming up, with one forecast, maybe you're off by an hour. With another, you're off an hour the other direction. If you average those together, you're more likely to get a more accurate timing of that wind ramp. And so often folks utilize, fairly large ensembles of many different models or model instances, and then combine those together in order to create a forecast. Next slide, please. So where do forecasts actually get utilized within the different aspects of power system operations? So we have those very short timescales, the intra-hour type timescales that are usually statistical machine learning methods. And these can be used, for example, for economic dispatch. As you move a little further out, maybe you utilize that for, say, a reliability unit commitment run, or dynamic reserve setting even. As we move into that medium term, the sort of day ahead, this is really where a lot of the value is derived, especially in market type operations at the day ahead, 2 day ahead time scale. Generally, these have a basis of numerical weather prediction models, and then you statistically correct for those afterwards. But these are one of the more common applications that really plugs right into that unit commitment economic dispatch process. But some of these forecasts from NWPs can go out even longer timeframes. And so you can see things going up, say, a week ahead. This can be used for generation planning and outage and maintenance and things of that nature. And so, for example, maybe you need to do maintenance on a particular solar plant, right? But you have a week out, 7 days of sun coming up, and so you don't want to take it out during that time frame. Maybe you want to wait until there's a bit more cloudy weather, for example. A couple other things that can be used operationally are things like ramp forecasts. So this can provide situational awareness to operators, just knowing that there is some expected uncertainty in the next hour or two. And so maybe you have additional reserves ready, or you're just paying a little closer attention at that moment. And so this is another way that forecasts, especially in the short term, can be utilized for situational awareness. Next slide, please. And so really just to sort of sum all this up, the basis for most of these forecasts are numerical weather prediction models that come from many governmental or say national meteorological agencies or some other larger consortiums like, for example, the European Center for Medium Range Weather Forecasting, or ECMWF. These themselves are informed by weather data and wind and solar generating plant data. And so the better data quality and the closer data you have to real time, the better forecast you're going to get. And so having up-to-date data, not only to go into the numerical weather prediction models, but also to help utilize those statistical methods for correction or for very short-term forecasting is absolutely critical. Now, sometimes this is produced in-house by, say, an ISO who have a team doing this. Sometimes this is produced by commercial vendors, but eventually that gets translated from the meteorological variables such as wind speed and solar irradiance to power prediction and actual megawatts or megawatt hours. Next slide, please. And so I just want to talk really quickly about some recent research on probabilistic forecasts. So probabilistic forecasts are, a little tougher just to get a benchmark for what actually makes a good forecast. And so we did a little bit of work looking at a couple different benchmarks that are commonly utilized in the academic literature and sort of how they apply. So first we have climatology, and this is all for solar forecasting. And so the problem here with climatology, like we were talking about earlier, it's very reliable because you're looking at essentially a whole history of what's occurred, but it has no resolution, right? It can't differentiate in the diurnal sort of cycle of solar, for example. You can get some other methods that have inspiration from deterministic or point forecasting sort of baselines like persistence, where you take, say, the last 20 days at a certain hour and utilize that. Again, it has pretty good reliability, but it's not that sharp. You can utilize the input directly from, say, a NWP model, like a 50-member ensemble from the ECMWF, and this tends to be very sharp. Unfortunately, it tends to be a little too sharp. The numerical weather prediction models are a bit under-dispersed compared to what actually happens. And so often you need to actually the forecast uncertainty is a little too narrow, and so you need to stretch that out, because sometimes we're really worried, especially with probabilistic forecasts, about those extreme events. We want to make sure we get those with good resolution, something that has a very big impact, but is less likely to happen at any one time. Next slide, please. And so just to give you a quick overview, of some methodology that we've developed at NREL through a Department of Energy and the U.S. Solar Forecasting Project over the last few years. We've been utilizing Bayesian model averaging techniques in order to post-process numerical weather prediction models. And basically what we can do is we can take a raw ensemble and we can make it much more reliable. So basically, so that if you say something's going to happen 1% of the time, it happens 1% of the time. And we can do that without sacrificing sharpness or being overly sharp. And so regularly we found that this technique outperforms some of the more common techniques for ensemble processing, such as just ensemble model output statistics processing. And I mentioned earlier the continuous rank probability score, which is a proper probabilistic metric. And so you can see much better behavior according to those metrics that we utilize there, especially in the tails of the distribution, which are really critical for power system operations, making sure that we get those extreme events reliably predicted. And so with that, I'd like to thank you for your attention, and we'll move on.
Thank you very much, Dr. Bri-Mathias, for sharing with us on the overview of the advanced renewable energy forecasting. Apologies, I was disconnected before. For all participants, if you have any question, please write it in the Q&A section. And next, I'm very pleased to invite Mr. Lynn to share with us on the update of the Vietnam power system and renewable energy forecasting in Vietnam. Mr. Lynn, time and screen are yours.
Hello to all of you who are watching this webinar. I'm Brodrick, an engineer from EVN NLDC. My company is responsible for operating the electricity system and electricity market in Vietnam, just like AIMO in Australia. The Department of Renewable Energy Management is a new established unit in NLDC to cope with the challenge and the explosion of renewable energy has brought to Vietnam electricity system. Today, I'm pleased to participate in this webinar organized by GPST and have a presentation on advanced renewable energy forecasting in Vietnam. Next, please. My presentation consists of two parts. The first part is some overview of electricity information from Vietnam, and the second part will be focused on today's main topic on the fields of renewable energy forecasting in EVN NLDC. Next, please. Let's go with me with the first part next. Up to now, the total installed capacity of Vietnam electricity system is more than 73,000 megawatt, with a variety of traditional source as well as the renewable energy. With considerable hydroelectric potential, we have about 25% of large hydro power plant, of which the largest is a solar hydro power plant with for 2,400 megawatt. However, to meet the strong growth in the load demand in recent years, we also have to rely on a fossil fuel source, in which coal-fired power plant has about 24,000 megawatt, accounting for about 33% and mostly concentrated in the north and the south of Vietnam. In addition, in the southern region of Vietnam, we have additional types of gas turbine and oil thermal power plant with installed capacity of about 7,002 megawatt and 1,500 megawatt. Respectively, along with the important driving factor that technology has developed, causing the cost equipment production to fall very rapidly, renewable energy resource has impressive growth in Vietnam. In 2019 and 2020, record the strong development of the both large-scale farm and small-scale rooftop. In just 2020 alone, about 12,000 megawatt of solar power were put into operation in Vietnam. Currently, the solar farm accounts for about 12% in the system installed capacity with nearly 8,800 megawatt, while the rooftop also played an equally important role with 11% and about 8,300 megawatt respectively. Small hydroelectric tide or runoff river plant still have grown steadily over the years, and so far about 4,700 megawatt has been connected to the system. Meanwhile, biomass electricity has not yet changed much through the years. Wind power, although currently not accounting for a high proportion, with only about 1,000 megawatt is expected to be the main drive for the increase of renewable energy sources, with many projects coming into operation in the last month of this year as planned. Next, please. Hopefully, a little overview of a system will help you more understand about the current status of Vietnam electricity system. I will present the content directly related to this topic of today's webinar on renewable energy forecasting in Vietnam. Please, next. First of all, I would like to talk about the role of renewable energy forecasting data in the operation of power system. At NLDC, the Vietnam Mid Electricity System Dispatcher, we use forecast data from the plant and NLDC source equipped for the operation. Final forecast will be selected from the plant or NLDC to obtain the selected forecast. This option will be used for both state of scheduling for the next day, the next interval, and the real-time operation. In normal operating situation, renewable energy will be prioritized to be mobilized maximum by the primary energy according to the government policy of Vietnam. However, when there's a projection that leads to real-time curtailment, we use the AGC system to control the capacity of renewable energy plant. The system uses a selected forecast calculated every 15 minutes, every 30 minutes interval as a basis of control of the power generation of the plant equally in the condition of curtailment. Next, please. For forecast data sourced from the plant side, we built a portal for the plant to publish or declare the information and update data continuously. The data update for any interval will end 35 minutes before the last interval, so that the selected forecast will be used for the next interval scheduling calculation. In the event that the plant does not need to update the forecast, the default value will be the day-ahead value. Next, please. For NLDC forecast data, we currently use both the purchase data from commercial vendors and the forecast data developed by and operated by NLDC ourselves. In response to the overheating renewable development from 2019, NLDC has conducted the international bidding to select the forecast data provider. In 2019, we have the Seoul Gas Agri-Weather joint venture. In 2020 and 2021, SolarGas is our main partner. From the international experience of other operators from all over the world, from 2022 onward, we will use forecast data from 2 independent suppliers. We have now completed the first supplier selection procedure. The bidding to find the second supplier will be finished from now to the end of this year. In addition, NLDC also invests in equipping a renewable capacity forecasting system. The system has been completed since March of 2021, approved by event to put into operation from the July of 2021. In addition, this is a power generation forecasting system using AI or machine learning model trained by NLDC with the input that are the forecasted meteorological data purchased by NLDC from a commercial supplier. In 2022, we expected to continue to update this system with more different model and forecasting method to make the system more complete. Next, please. For NLDC current commercial supplier forecast data, the company, they use the meteorological input model from many famous forecasting agencies around the world, include the GPST model from NOAA, for forecast up to 14 days, the IFS model from ECMWF and Icon from DWD forecast for the next few hours to the next few days. For forecast over the next few hours, they use satellite image data primarily to deliver the forecast result on relative, and the forecast result is very good quality, and they have supplier and support us a lot in the real-time operation. Next, please. Here's an overview description of the forecasting system developed by NLDC investment. This system has four main functional blocks: train application, management application, forecast service, and schedule service. Functional blocks are closely related to each other and work on the central database. It started with the train application. This app is an interface that allows the operational engineer to get the operational data from the historical operational data from the plants using LSD and recurrent neural network to train the model. The trained model will be transferred to the management application for management and stored on the database. Management application is not only manage the model, it's also manage the forecasting schedule, as the forecasting needs to be continuously updated. We make periodic forecast for the next 14 days and 3 days, once a day. Forecast for 12 hours ahead is execute every 15 minutes, every 10 minutes, sorry. All the forecasts are at the resolution of 15 minutes. Schedule will be operated by the schedule service. The service scans the periodical calendar, take the train model as well as the input for forecast from the database to send to the forecast service, and then receive the forecast result back and write this result to the central database. And the forecast service is the operational heart of the system. Our engineer developed a Python Flash server with a key technology platform to operate the LSTM model based on Google TensorFlow platform. In addition to improving the accuracy of the forecast, we also use the real-time plan operational data to calibrate error through the linear regression model. Next, please. This drawing shows the image of the application in the system, including the train application and the management application. The interface are designed to suit with our own need, making the management operation on the app relatively convenient and easy to use. Next, please. In addition to the forecasting system, we also developed the system to operate monitoring the system, including the system scale operational monitoring for different types of forecasting data from the plant, from the supplier, from NLDC system, the selected forecast and real-time operational data from the plant. In addition, the real-time operational data have own power type of the real-time operation is also managed on the interface. Next, please. For the operation management of HRE plant, we also have our own tool to implement. On this tool, the information is displayed in full, including the forecasting data from the plant, from the supplier, from NLDC system, the value of the forecast as a selected forecast, and the value of real-time power of the plant. In addition, the forecast and actual meteorological data of the plant is also shown in this tool. Have the renewable operator to make the decision more precisely. And next, please. I hope my presentation has helped you have more information and understanding about how Vietnam's electricity system, as well as the forecasting in renewable energy in Vietnam in general and in NLC in particular. I would like to finish the presentation now. Thank you for the attention.
Thank you very much, Mr. Lynn, and for all participants, if you have any question to Mr. Lynn about renewable energy forecasting in Vietnam, please write it on the Q&A pages. Last but not least, we will have a joint presentation by AEMO expert, Mr. Jack Fogg and Mr. Joshua Brodrick. Time and screen are yours.
Thank you, Beni. And yeah, very happy and honoured to be here today. So on behalf of Josh and myself, we'd like to thank you for inviting us to have this opportunity to talk about renewable energy forecasting at AEMO. Next slide, please. So a bit of context about the Australian electricity market. Josh and I are members of the operational forecasting team at AEMO, and we're responsible for short-term forecasting of load, wind generation, and solar generation. We are responsible for the national electricity market, which is the East Coast grid in Australia. There's a separate grid on the western side of the country and in the northwest as well, but they're not interconnected to the national electricity market. What you can see there is it's quite a sparse, stringy grid. It's one of the longest interconnected power systems at over 5,000 kilometers, but it isn't very highly interconnected. It's quite a stringy grid. We have over 450 different participants in the market, from retailers to generators, and we've had quite an increase in the number of wind generation and solar generation participants as well. The peak load of our grid is around 36 gigawatts, and minimum loads are 15.3 gigawatts, and falling as well because of the penetration of rooftop PV, which I'll discuss in a future slide. We have about 59 gigawatts of generation capacity, and over 10 gigawatts of rooftop solar is not included in that grid scale capacity number. Next slide. This is probably not a uncommon sight. We're experiencing quite strong growth in the amount of utility scale wind and solar generation capacity. You can see quite a large intake in uptake in 2018 of solar farms, and that's continued. And this is posing quite a few challenges to our system operation. So yeah, putting that in context, over 12 gigawatts of wind and solar on a peak system demand of approximately 36 gigawatts. And on the next slide, we'll see rooftop PV. So you can see there over 10 gigawatts now of rooftop PV. So this is solar PV systems installed on people's houses. It's effectively behind the meter from our perspective as a system operator. And what it does is it causes the duck curve that most people would be familiar with in the middle of the day on sunny days. In our case, in some of our jurisdictions and regions, that duck curve is getting very low and approaching 0 megawatts in the middle of the day. This does pose quite a number of challenges for us as a system operator, which I'll touch on. On to the next slide. So for the reasons that Bri-Mathias outlined at the start, renewable energy forecasting is very important for us at AEMO. We've invested in a number of different systems going back to 2008 when we we invested in the wind energy forecasting system. I'll be touching on some more details of these individual systems on the next slides. In 2014, we created the solar energy forecasting system, and it's pleasing to know that the methods that we're using, which include statistical models and physical models, are actually quite consistent with what Bri-Mathias was outlining at the start of this session today. These systems produce automated forecasts every 5 minutes. And we've also recently allowed participants, so wind and solar farms, to submit to us their own forecasts. The idea behind this was that wind and solar farms do have the ability to have more information on the local conditions at their wind or solar site, which would enable them to create a more accurate forecast for dispatch, for economic dispatch. So that's the 5 minute ahead forecast. There's a few links on this slide. So when the slide pack is shared, you can click on those links to find out some more information. The next slide, please. So for our utility solar generation forecasting, we use a number of different inputs which we require when solar farms are registering in our electricity market. There's some static information which relates to whether the solar farm is a tracking or fixed axis solar farm, what types of modules are installed, what types of inverters are installed, the location, and the other relevant local information for that site. We then also require real-time telemetry information transferred via the SCADA system to our control center. This includes solar irradiance, horizontal and inclined irradiance, as well as temperature information from local weather stations installed at the site. We also use numerical weather prediction information for the longer horizon forecasts. We're using the ECMWF model as well as the GFS model. And then we're also using satellite imagery from the Himawari 8 satellite, which updates every 10 minutes and provides up to 1.5 kilometer spatial resolution. These go into our model and we produce an output, which is the mean forecast, as well as a statistically adjusted most probable forecast, which is the POE 50. And then we also produce a POE 90 and a POE 10 forecast, which gives us an idea of the uncertainty. Next slide, please. For utility scale wind generation forecast, it's quite a similar story, but obviously specific for wind farms. So we require information when the wind farm is registering to connect to our system, what type of wind turbines are installed at the farm, the location of them, and the size in installed capacity in megawatts. We require real-time data as well via SCADA, and that includes nacelle anemometer measurements of the wind speed and other relevant weather information from on-site weather stations. And then we also use numerical weather predictions, again, the same ECMWF and GFS models. The outputs are similar, an average forecast, a statistically corrected most probable forecast, and the POE 90 and POE 10 forecasts as well. Next slide, please. Rooftop PV forecasting is very important for us. It has a significant impact on the accuracy of our load forecast. And because the rooftop PV systems tend to be installed in the quite highly populated load centers of our cities, when there are cloud events that affect those cities, they can cause very large fluctuations in the rooftop PV generation. This poses challenges for our real-time operations to maintain secure operation of the system and to ensure we have sufficient reserves for any contingencies. To create the rooftop PV forecasts, we've used input sampling measurements from systems spread out all around Australia. We currently sample from about 35,000 systems, and those are spread across different cities and postcodes around our country. We use those samples together with the installed capacity information from our regulator, to upscale those measurements to produce an estimate of the rooftop PV generation for that geographic area that we're looking at. This is combined with the numerical weather prediction, again, ECMWF and GFS, as well as satellite imagery from Himawari 8 satellite. That produces, again, the same set of outputs, the most probable forecast and statistically adjusted POE 90 and POE 10 forecasts. The next slide, please. So how does AEMO use these forecasts? These forecasts feed into a number of different system and market processes which we use to operate our grid. So starting from the longer term horizons, we use forecasts of wind and solar generation, as well as rooftop PV, together with information on network outages and generator outages, as well as our load forecast, to perform a resource adequacy assessment at the 36-month ahead horizon. This process allows us to know whether planned network outages and generator outages need to be rescheduled to ensure that we have sufficient supply to meet the expected demand. As we get closer to real time and we move into the 1 week ahead horizon, we have more accurate weather forecasts. And so we're able to run this process again to see whether supply is sufficient to meet demand in the 1 week ahead horizon. We rerun this process every hour to ensure that as conditions change with the weather forecasts and our wind and solar generation forecasts, or if generators and network outages are changed, we're able to reassess that regularly. When we move to the one day ahead horizon, we use forecasts of wind and solar, as well as load and generator bidding, to publish an expected price and dispatch schedule, which is used by the market, such as generators, wind and solar farms, and market participants, to do day ahead fuel purchasing decisions or commitment decisions. We rerun this again as we get closer to real time. So 1 hour ahead, at 1 hour ahead, we run this process every 5 minutes so that we're able to use the most recent data and the latest forecasts. And then for economic dispatch, we use real-time forecasts of wind and solar and load, as well as the most recent bids and availability of generators to dispatch the fleet according to any constraints that are on the network and the expected load. Next slide, please. One thing I want to mention as well is that if there's one message that I want to get across today, it's that understanding of uncertainty is extremely important for grid operation when you've got increasing and very high penetrations of renewable energy. Just recently, we actually surpassed 58% of our total electricity supply coming from renewable energy sources, which I think is a very high achievement for a grid of the size of Australia's national electricity market. And our CEO has actually set an optimistic goal to achieve 100% renewable energy instantaneous supply by 2025. This does pose very important challenges around making sure that we understand the uncertainty around the forecasts of wind and solar, as well as load, to ensure that we are able to manage the risk when the forecasts actually, or when the observations deviate from the expected forecasts. We've had a few challenges recently, and these are what we would consider emerging challenges. I don't think that these are highly researched and well known amongst academics and researchers looking into system operation. High temperature wind turbine cutout and derating affected us 2 summers ago when we had very, very hot temperatures during our summer, as well as high winds. And during that situation, we had quite high output from the wind farms. But because the temperatures were so high, the internal control systems were derating the turbines and in some cases cutting them out for safety protection because the internal temperature sensors were so high. This is a very challenging event to try and predict accurately, because you have multiple different vendors selling wind turbines and they've all got different control systems. And there are multiple temperature sensors being used to protect the turbine from overheating. In other cases, we've also found that the installed turbines are actually upgraded after they're installed in Australia because there are unique cooling requirements in this country. And so the actual performance of the turbines does not meet the specification sheets that the OEMs provide. Another challenge is bushfire smoke and dust storms. Last summer, we had a very severe bushfire season in Australia, and we saw attenuation of solar farm output as well as rooftop PV output due to the smoke that was in the air. We actually worked with a partner to publish a document that's linked there. So you can have a look at that to read more information about the attenuation of large-scale solar due to bushfires. And dust storms are also a challenge. Particularly recently, we've had very dry summers, and when the winds pick up, we can see a lot of dust traveling across the outback in Australia, and that poses a challenge to solar farm output as well. I'll now hand over to Josh, who's going to talk about some of the data science developments that he's been working on.
Thank you, Jack. And again, just to echo your sentiment, thank you very much for having us and giving us the opportunity to present to you today. So I'm briefly going to touch on a number of tools that our data science team have developed. Today, we'll focus primarily on situational awareness. So we won't focus too heavily on some of the machine learning techniques that we employ. Today's focus is on some of our situational awareness tools. And again, a lot of these are prototype tools, so please don't judge them too harshly or share them too widely if that's okay. So on this very first slide, this is not directly related to our renewable energy forecasting. However, it raises a key point on error attribution. So this is actually our operational demand forecasts that are in the upper section of the screen. And for those, we perform a key process of error attribution, where we run the models post-fact and determine what produced divergences in our forecast. And a key area that we like to focus on, as can be seen on the slide, is the error that we attribute to our renewable energy forecasts. So in that example there, sorry, give me 1 second, I'm just having an audio issue. Hopefully everybody can still hear me okay. So yeah, audio's back, thank you. So error attribution is very important for us, and the ability to understand where the error in our models comes from allows us to focus our resources on key areas for improvement and targeting what we refer to as the lowest hanging fruit. So in that example, just talking to our operational demand, we not only attribute error to the models themselves, but a number of input factors. In this case, the rooftop PV forecast errors, the non-scheduled generation error fleet, and the weather forecasts themselves. So that was just a brief. So our in-house data science team, and if you could flick to the next slide, please, that would be good. Our in-house data science team has developed a suite of tools which support both our analysts in our team and our control room staff in their decision-making processes, as well as outage planning and risk assessment. I'll briefly touch on two of those tools today. So the first one is what we refer to internally as a wind at risk tool. So you would have heard Jack in that previous slide talking to some of the emerging issues we're facing, and one of those is the wind fleet essentially derating or reducing its output to zero as a result of high wind speeds or high temperatures. So in order to assess the forecast and the magnitude of risk we may face, the initial piece of work we have to do is assess what those various cutout thresholds may be. So to do that, we do a fair piece of historical data analysis, but we also work closely with the manufacturers and farm operators to try and understand as much as we can about the equipment that is in situ and get as best information as we can to, as Jack alluded to in the previous slide. In this case, we then make use of high resolution gridded weather models to extract highly localized weather forecasts for each wind farm. And we assess those against the generation output for each farm as produced by our AWS models that Jack touched on in some of the earlier slides. So in the example, as you're able to see on the screen, and again, you'll be able to probably zoom in this slightly more on the slides post-fact, you can see we have multiple numerical weather models available to us. So we use ECMWF as well as the Australian Access-C models. Both of those have different forecast horizons. So one's a more near-term model, one looking out slightly further ahead, and they have different temporal resolutions. We are then able to essentially attribute the risk of megawatt derating to both temperature and wind speed causation factors. And we initially do this at a regional level. So that first slide is, I guess, demonstrating in our New South Wales region what a simulated risk of megawatts derating would be over the next day or two. Next slide, please. We are then able to drill down further to an individual farm level and assess this on a case-by-case basis to really focus on the key farms that may pose the greatest risk of derating or cutout, which is demonstrated on the next slide. And if you could skip to the next one, we're also able to assess the various gridded weather models at each particular wind farm and change the various thresholds that we feed into the model. And we're also able to visually assess how close to said thresholds the forecasts may be approaching. So a key point here is, while in this case, this tool does not necessarily make use of highly sophisticated AI or ML models, it still provides very useful information to analysts and controllers for risk assessment purposes, particularly for safely managing the grid and dealing with ramps in renewable energy generation, so that they have a sufficient backup plant on hand to be able to manage the change in loads as those farms may ramp up or down. One other tool, which I'll touch on briefly, is what we like to refer to as our live map, and that is on the following slide, if you were able to change. So this interactive map allows for overlaying our transmission and generation infrastructure with near real-time weather station information from right around Australia. So we have streams from the Australian Bureau of Meteorology, and for about 500 weather stations around the country, thereabouts, we receive a near live stream of data at a 1-minute interval. This is then fed into our map and updated. And we have a number of weather constructs available to us on our map, you know, temperature, wind direction, wind speed, humidity, the full gamut that comes from those weather stations. So if you, that particular slide, for example, is just showing a visual representation of the current temperature around the country. If you're able to change the next slide. A key use for this tool that is, I guess, the primary reason we developed it is to track specific weather systems, or what we refer to as cool changes, as they move up the southeast coast of the country and have a significant impact on major load centers. So that particular image shows the southeast corner of Australia, with Melbourne being one of the second largest city in Australia, and hence the second largest load center. So Melbourne is often referred to as a city which can experience all 4 seasons of the weather in one day. And this obviously, again, has a very large impact of the underlying grid demand in the region. So for an example, in summertime, Melbourne could be experiencing daytime maximum temperatures in excess of 40 degrees during the day, before a very sudden cool change weather system sweeps across the city and temperatures can plummet by up to 20 degrees in a matter of minutes. So the timing of these changes is something which many weather forecast models struggle to predict, even if they are able to predict the daytime maximum minima correctly. The timing is something they often struggle with, especially when it's, you know, mere minutes can make quite a large difference in our underlying demand forecasts. So if the timing of a weather change is expected to occur around the time of our system peak, it can obviously have drastic effects on the accuracy of our load forecasts and how we manage the grid and our generation fleet. So since the advent of this tool, we're literally able to watch the cool changes move up the coast in near real time. We also have an embedded meteorologist in-house in our team, and using his expertise in conjunction with this tool, we're able to provide far better estimates to our control room around the likely arrival time of these cool change events, and also the anticipated effect on temperatures at these major load centers. So that's proved key to us over the last summer. And again, this just serves to illustrate the benefit of a wider range of tools that we have in forecasting. So not merely the deterministic forecasts that we were spoken to earlier in the presentation, but we also obviously make use of probabilistic forecasts, which Jack has touched on, and then a number of other tools for situational awareness as well. That concludes our presentation, I believe. Thank you very much.
Thank you very much, Jack and Josh, for your presentation about the situation in Australia and the work AIMO is doing. Now we are in the Q&A session. I would like to thank all of you for have already wrote your question in the Q&A feature. Some of the questions have been responded as well by our expert. All other, if you have another question, feel free to write it in the Q&A box. But I will start the discussion with one question from the audience to Dr. Bri-Mathias. Earlier in your presentation that you mentioned, there is a critical need to balance between load and generation and all time instantaneously. So from your point of view, from your experience, and how do you see the challenging for the system operators to do this balancing?
Sure. So that obviously really depends on the system we're talking about, right? There are power systems that vary worldwide quite a bit. You know, in many of the countries that we've talked about here today, the system works by allowing load to do more or less whatever it wants, and you turn on supply to match that, right? In the Indian power system, for example, it's kind of the opposite. You run supply flat out and adjust load to meet that, right? And so it's, you know, it depends on the challenge of the system. So when we say instantaneously in the power system, we mean at, you know, sub-cycle levels. And so that's why we hold lots of reserves in the system, so that when a plant goes out, there's enough capacity to bring the frequency back up to nominal, or, you know, a safe operating frequency, at least pretty frequently. As we put more renewable energy on the grid, the challenges become, you know, a little different, because the system was designed for large scale plants that could be turned on and off, but would have, you know, generation failures from time to time. And so as supply becomes a little bit more variable as well, there are a lot of things that can help that. Forecasting is one of them. You know, storage has traditionally been very expensive, but has become much more cheaper in the last decade or so, and also provides a great sort of leveler there. And so it really just depends on the system. Really every generation makes it slightly different. For one system, it may be, you know, that the challenge is you have a very variable supply. Another one may be that you have a very, you know, solid supply, but it's not flexible enough. It can't ramp up and down as quickly as needed. And so, yeah, every generation makes some load patterns a little bit different, but those are some of the patterns that we recognize.
Thank you very much. Right, and just pass it to Jax or to Joseph. We have a question that asking, what role can cloud technology play in the forecasting? Or maybe you have experience as well in AIMO.
Yeah, we recently in 2019 added satellite imagery to our solar forecasting system. Prior to that, we weren't using satellite imagery, and so we weren't able to do cloud motion vectoring or any of those new techniques. That has proved to be a significant improvement in the forecast accuracy. I will caveat that and say that certain conditions are still very challenging, even with the use of high resolution and rapidly updating satellite imagery. For example, you can have clouds at different layers of the atmosphere moving at different speeds in different directions, and cloud formation and dissipation as well is quite challenging. So yeah, cloud technology plays a very important role in solar forecasting.
Thank you. We have a follow-up question. I think I'm sticking with Jack as you're presenting about the solar forecast earlier. We have a question. Is there a limit for the solar install or penetration into the system? If I can return back to you, Jack.
Sure. Yeah, that's a very interesting question. We may be approaching some sorts of limits now in Australia, because, as I mentioned, in certain areas of the country, we're approaching zero minimum demand in the middle of the day on sunny days, which is very challenging for us to operationally manage the grid under those situations. So we may be approaching a limit. There's no technical limit, or, well, sorry, there's no theoretical limit, but technically there are challenges that may impose a limit. So yeah, interesting question.
Thank you, Jack. Maybe I also would like to invite a comment from Mr. Lynn, because as you mentioned earlier in the slide, the solar portion in the install capacity in Vietnam is very significant. And if we look to the historical, the solar in Vietnam is really soaring for the last 2 years, right? That could be so. Maybe it's the same question. There's also the limit that that you will able to absorb solar into the system, Mr. Lynn.
Thank you for the question. And following my knowledge about the power system, I think that the limit is just in operational condition and not in the limits in the policy. I think that Vietnam, we welcome the renewable energy for the development of the power system, because in the future, we still have to rely much on the renewable energy to meet the requirement of the demand. But with the current condition of the grid, I mean the transmission or distribution grid system, in some time of the day, we cannot manage to absorb all the power from renewable energy. That leads to the curtailment, but it just in some time of the day and some time of the year, not for the whole times of operation. And I believe that this situation will finish in a very short time, because you know that the development of Vietnam economic is grow fastly in recent years, and so that we need a lot of energy, especially in the renewable energy. So I believe that the curtailment is not the story of the future of Vietnam power system.
Thank you, Mr. Lynn. Dr. Bri-Mathias, that if I can connect it back to you on the earlier question about the balancing, and the issue is question on the limit and the concern of the balancing. Would you mind to share your view on this question as well?
Sure, happy to. I think it depends very heavily on the system we're talking about, right? If you have certain distribution grids, for example, you may run into a local limit on a distribution feeder, right? That's going to be very different than at a system level. And it just depends on the technologies that you have available at your disposal, right? If you had communications and visibility into every behind the meter, PV system, they wouldn't be behind the meter anymore, right? But it would give you the ability to, have some control of those. And that's a much different story then about what happens than if you don't have the visibility into that, right? And so, some of the limits that people often talk about have to do with the stability of the power system. And so, the aspect there is that almost all installed solar today has what's known as a grid following inverter, which is not like a synchronous generator, and so doesn't naturally provide support to the system when there's a change in load or generation by the Newtonian physics of the generator. However, there's a lot of great research going on in what are known as grid forming inverters, which actually, have a wider range of flexibility, but you have to tell them what to do, right? So you have to be able to have digital control methods that can provide the right response at near instantaneous timescales over a wide range of conditions. It doesn't happen just sort of automatically because of the physics of the generator. And so there's solutions there, but it does require more research and implementation to really understand, all the challenges associated with it and, what response can be provided.
Thank you. I began with a question from the participant that I think it's back to Jack or Josh. I'm back again talking about the solar and rooftop PV. That's how to accurately predict it. Accurately predict not only the weather but also whether the rooftop solar is running or not. Then because it will be impacting your forecasting as well. That how to accurately, I'm not sure that we can use it, accurately predict, but maybe I have an opinion on that, Jack or just.
Yeah, what we do in Australia is we sample from a number of systems to get an idea of what the generation is. So it becomes more of a sampling question. So provided that your sample is representative of the entire population, then this methodology should be reasonable and then probably should be accurate. But yeah, there are assumptions baked into that around shading of panels and orientation of panels and tilt of panels and operation of them as well. Like, are they running still? Maybe the inverter had an issue and it's been decommissioned or replaced, or a lot of assumptions. But I think from our perspective with the system we've developed, it's generally fit for purpose for the use that we need it for, which is to feed into our load forecast to try and improve the accuracy of our load forecast. But yeah, if your requirements were slightly different and you needed to know exactly what the behind the meter rooftop PV generation was, then maybe this methodology is not the most appropriate. Josh, anything to add?
Probably also worth adding that in order to have the statistical significant sample method work, you need to have a good idea of your overall installed capacity as well. So we have a system in Australia where new rooftop systems are installed in Australia in order to get, I guess, essentially rebates from the government. Those systems are supposed to be registered with the government, and there's a body that collects said information. Now, that information, again, is not perfect, as you can imagine, with such a large scale and being logged by so many multiple installers. There's obviously issues with that database as well, and where the systems have been decommissioned and replaced after hailstorms, for example. So, as Jack mentioned, there are some assumptions and limits with it, but it's essentially a combination of sampling real-time data from a number of systems that have that capacity to send that telemetry in real time, and then having a pretty decent idea of what your overall capacity is to be able to scale it up. And then, as Jack said, ultimately, we really only use the output of that solar rooftop forecast as an input to our demand models. So it's output as an input as opposed to being the primary definitive output that we look at.
Thank you, Jack and Josh. We have many follow-up questions from the participant on this topic. Particularly, it's also interesting asking what data is taken in this forecasting. So if I can read it from the question is, they would like to know what data is taken specifically on several points that you mentioned. One is a numerical weather prediction. Second is the solar farm info. Third is the real-time data from the solar farm. And fourth is satellite imagery. From where? So it's more the question is what data and from where the data is being taken. If I can pass back to Jack and Josh on that question.
Yeah, so from the numerical weather predictions for solar forecasting, we use the irradiance. For wind forecasting, we were previously using the wind speed and direction forecasts at different levels of the atmosphere. We recently, just last year, changed that to use a new level which ECMWF are publishing, which is, I believe it's equivalent to 100 meters above ground level. So that's pretty close to turbine height. So we're using that. We also use some other values from those NWPs, but they're probably less significant. I wouldn't say that they're the most significant ones that we use. So what was the second question, Beni? Sorry, I've forgotten, and I think I've lost it. Screen.
I think it's also disappeared, but it was on the solar farm data. So solar farm was the metadata, and then the second was the live data that comes from the solar farms themselves.
Yes.
Yeah. So in terms of the solar farm information, we require the solar farm to provide us information on the type of module that's installed, the tilt and orientation of that module or the set of modules, whether they're fixed panels or if they're tracking panels and single axis or dual axis, we can cater for both. The inverters, and then information like the total number of solar modules, how many modules are connected to each inverter, the DC to AC ratios, sort of standard information that you're required to set up a solar model. In terms of the real-time data, we require pretty standard things like active power from the solar farm, the control system set point, so are they actually curtailing themselves or down regulating, any local limitations that might be in place at the farm, and then we require some telemetered weather information, so inclined and horizontal irradiance, and then a number of different weather concepts, including temperature from on-site weather stations. And then for the satellite imagery, we use data from the Himawari 8 satellite, which is a Japanese satellite that was launched, I think, 5 years ago or so. Hope that's answered the question.
Thank you, Jess. There's a question on the grid level battery. I think I pass it to Dr. Bri-Mathias first. That question is: having grid level battery to be a disruptive or much needed assistance to the forecasting?
I guess it depends on what you mean by grid level, right? So if it's in the distribution grid and there's lots of them at the household level and they're changing your load patterns and you don't have that in your historical data, right? Then that could present some sort of potential issue. Most of the time though, they are helping in that, they'll, if you mean by grid level, they're participating in the market at the transmission level, right? Then they're getting a price signal that's going to essentially cause them to help with balancing problems, right? They'll be more likely to charge at times when there's a low price and discharge at times when there's a high price. And so, a lot of things we're seeing are batteries that are just serving as quasi generation sources, if you will, on the transmission level. A lot of hybrid power plants, of say wind or solar and storage. And so those can change the generating profiles, but it also gives you a lot more flexibility in the system. And so I think the key aspect there is just knowledge of the system specifications, as has sort of been alluded to here, and the trends of the operating patterns and how those might change.
Thank you. And back to Mr. Lynn, that's going to be the role of forecasting in the operation cost. So everybody is asking about the dollars. So the impact in the reduction of electricity tariff. Is that exist? I mean, is that real in your experience, Mr. Lynn?
Okay. I think that is a very good question for us, especially for the dispatcher. It's clear that the forecasting data plays a very important role in operation with a very large share of RE like in Vietnam. In order to minimize the capacities, minimize the curtailment, we have to make every effort to ensure that the forecast is as accurate as possible. Along with the loss forecast, we will come up with a plan, operational plan for the other conventional sources. The most accurately, any error for the renewable energy forecast will lead to the risk that the system being surplus of power or deficit of power that leads to more curtailment for the renewable energy or make risk for the power system. And I think that will increase the cost of electricity or increase the tariff.
Thank you, Mr. Lin. I mean, from consumer, the tariff reduction is very much the issue. Thank you for responding to that. We almost end, and I think we have one more question if I can address back to Jack and Josh. In which way have you experienced the increased ability to integrate renewable energy with improved forecasting? I mean, are we looking maybe need less reserve, less curtailment, or less blackout?
Yeah. So improved renewable energy forecasting so let's start from the very short-term time frame of dispatch and frequency regulation. If we have smaller errors due to improved renewable energy forecasting, then that reduces the use of frequency keeping regulation services. So that has a direct impact on the cost to operate the system. If we can know that our forecasts might be more accurate in certain conditions, then we can procure more regulation services. And if we know that it's a sunny day and we're going to be quite accurate, then we can procure less. So really optimizing that procurement around how accurate our forecasts are and the uncertainty we expect can have direct impacts on how much renewable energy we can integrate and how cheaply we can do it.
Thank you very much, Jax. Thank you very much for all of the speakers and participants. I'm pretty sure that we learned a lot today, but unfortunately, we have come to the end of our event. As mentioned earlier, we will post the recording of this webinar in the GPST website. And to access the video and learn more about the Global Power System Transformation Consortium, please feel free everyone to visit our website at the global-pst.org or follow the Twitter at the global-pst, or you can also connect with our LinkedIn page. With that, allow me to end our event today. Once again, I would like to thank you, all of the speakers and all the colleagues who are helping the arrangement of this webinar, and more especially to all of the participants who joined with us today. Thank you, and see you again in the next GPST ASEAN Community of Practice. Thank you, and bye-bye, everyone.